Hello, this is Mrs. Scarple, and in this video I'm going to go over how you can do a quick graph of logarithmic functions. And let me get back. Here's where we want to begin. I want to start with just our basic log of base 2 of x. I'm just choosing to go with 2 just because we're going to have some smaller values as I plot some points. But I will finish by showing you how we do this for a log of a different base, because it does depend on your base which anchor values you will use. So you need to remember that log base 2 of x is the inverse of 2 to the x. Well, we can complete a table for 2 to the x power by plugging in values for x, and I'm going to use the values -2, -1, 0, 1, 2, and 3. Now when I take my calculator and I enter 2 to the -2 power, it's going to come back with 0.25 or 1/4. When I enter -1 for x, that's 2 to the -1 power. That's going to be 1/2. 2 to the 0 power, anything to the 0 power, is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Now these aren't the anchor values that I want to use. These aren't even the points I would use for log base 2 of x. Remember, this is the inverse of log base 2 of x. So if I want a table that represents the graph of log base 2 of x, I'm going to have in my first column x as my input. I'm going to write log base 2 of x is my output here. It will be my y value. And remember, with inverses and tables, you switch the columns around. So my inputs this time will be 1/4, 1/2, 1, 2, 4, and I should have written 8 instead of 3 over there, so let's fix that quickly. And then the outputs are what our original inputs were. So -2, -1, 0, 1, 2, and 3. So for our next few graphs, this is what I'm going to consider to be my anchor values for log base 2. Now let's plot these points. So when x is 1/4, we're going to be down 2. When x is 1/2, we'll be down 1. When x is 1, we're at 0. When x is at 2, we're up 1. When x is at 4, we're up 2. And when x is at 8, we're up 3. And then we connect these because a logarithmic function is a continuous function. And we keep growing. Now, on worksheets and other printed materials, it may look like this curve gets to exactly 0, but actually, this graph will not ever cross the y-axis. We have what's called a vertical asymptote here. Let me use a color that's showing up a little bit better. So I'm drawing some yellow dashes on my y-axis. We call this a vertical asymptote. What that means is we have a line that our function, our graph, is approaching, but it is never actually reaching. And every logarithm has a vertical asymptote. So you'll see here that we have this curve, we have a y-intercept at 1, 0, and that's something else you will see with every single logarithmic function. We have a y, or an x-intercept, excuse me, I said y-intercept, an x-intercept at 1, 0. And every logarithm, unless it's being shifted, unless it's being translated, will have that intercept. The other thing you'll notice is if we change our base, instead of going 1, 2 on our inputs for our logs, let's say it was a base 4, it would end up going 1, 0, 4, 1. So the point that we have right here that follows the intercept is always going to be the base value 1 every time. That also matches the distance between our vertical asymptote and our curve. So when we're up 1 unit from the x-axis, the distance between the vertical asymptote and our graph is going to match the value of the base of our logarithm. So now let's take a look at another graph. We have log base 2 of x minus 3. If you remember from our graphing of quadratics and our graphing of absolute value functions, this would indicate that we have a shift to the right 3. And that is also true for logarithms. We're going to shift to the right 3 units. What that means is my vertical asymptote, instead of being the y-axis, is now going to be at x equals 3. A vertical asymptote always has the equation x equals, and it'll match your shift, x equals 3 in this case. I don't have anything added or subtracted on the end, so I don't need to worry about shifting the x-axis for this particular problem. But if I think about my anchor values, and I'm just going to start with 1/2 this time. When our input is 1/2, our output is going to be -1. When our input is 0, I think I've just confused myself for a moment, so it's not going to be 0. When our input is 1, our output is 0. When our input is 2, our output is 1. When our input is 4, our output is 2. And when our input is 8, our output is 3. So it's that same table we had on the previous problem, with the exception of I didn't start at 1/4. So when x is at 1/2, so I think of my vertical asymptote as being my new y-axis, so to speak. So I'm going to count from this vertical asymptote, 1/2 unit, I go down 1. From that vertical asymptote, I go 1 unit to the right, and I'm on the x-axis. For the next point, 2 units is up 1. 4 units is up 2. And 8 units, so that was 4, 5, 6, 7, 8 units is going to be up 3. So we have that same shape curve that we had in the previous example. It's just that it's been moved to the right 1 unit. Let's take a look at our next graph. Here we're subtracting 4 after we evaluate the logarithm. That's going to be a shift down 4 units. What that means is our x-axis is going to shift down 4 units as well. So 1, 2, 3, 4. Our graph, our x-axis, slide down. Now, it's not that the x-axis is actually sliding down, but this is what we're going to use as the transformation of the x-axis. Our vertical asymptote is still going to be the y-axis, or x equals 0 is our vertical asymptote. When we do our table, and it's easier for me to write the outputs first, -1, 0, 1, 2, 3, and to think about what the input will be by thinking of 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So I'm thinking of the inverse, but writing my table in that inverse order. So from the vertical asymptote, 1/2 unit is down 1. Let me use a color here. From that vertical asymptote, 1 unit stays on that axis that's been shifted. 2 units from our vertical asymptote is going to be up 1 unit. 3 or 4 units from our vertical asymptote is up 2, and 8 units is up 3. So this graph has shifted up, or excuse me, shifted down 4 units. But we still have that same shape curve that we had before. So now what's it going to look like when I combine them? Think of it just like you did with the quadratics. This is going to be right 3 and up 2. So I'm going to start with that vertical asymptote, right 3. So that has the equation x equals 3. I keep stressing that because you will come across some problems that ask, what is the equation of the vertical asymptote? And then I write the wrong number. It's x equals 3. But we're also shifting the graph up 2 units. So that means our x-axis is being transformed, is being translated. And the point we're interested in working off of is the intersection of the translation of the vertical asymptote and the x-axis. I think of it as my new origin, my new starting point. We still use that same XY table that I did on each of the previous ones. So I'll have values of 1/2, 1, 2, 4, and 8. So from that new origin, right 1/2 unit will be down 1. From that origin, right a full unit stays at 0. From that origin, 2 units to the right is up 1. 3 units, or 4 units, excuse me, is up 2. And then 8 units is up 3. And this is the shape of our graph. So now, what happens if we change our base, like I have here? Well, I would still recommend doing an inverse XY table. Still use the values of -1, 0, 1, 2, and 3. And think of it as 3 to the -1 will be 1/3. 3 to the 0, so I'm using the base of the log. 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. 3 to the 3 is 27. Now, we may not be able to plot all of those points, but we have a good start on anchor values that we can use. I can also tell you that this is going to go left 1 unit, and it is going to go down 2 units. So let's draw a new vertical asymptote. That's going to be at x equals -1. We know that the x-axis is shifting down 2 units. We're focused off of using that point of intersection for starting any counting to our anchor values. So from that point of intersection, 1/3 to the right would take me down 1 unit. 1 unit to the right stays at 0. 3 units to the right is at 1. 9 units to the right, 4, 5, 6, 7, 8, 9 units to the right is up 2. And I don't believe, yeah, we're not going to be able to get 27 units up. So we'll use these points to draw our curve. And hopefully you'll notice that this one doesn't grow as fast. It stretches out more horizontally rather than growing vertically like it did with a base 2. But I do want to mention here, remember when I had said that if I go up 1 unit from where my lines intersect here, this distance is going to match your base. This is a distance of 3. That matches our base of our logarithm. So while everyone will always have an x-intercept at 1, 0, the next point will be the value of the base, or b, units from that vertical asymptote. And this concludes the video for graphing logarithmic functions.